Hello, welcome back to the channel where we are reviewing the principles and practices of commercial construction textbook. So this video is about chapter 6 and that is formwork. So let's begin. All concrete sections made with cast-in-place concrete require some temporary means of support for the freshly mixed plastic concrete. Whether the concrete is placed in a factory setting, as in the same of precast section, or cast on the building site, some means of support is necessary to hold the concrete in place during its curing period. So this temporary framing is known as formwork. So because of their temporary nature, forms must be designed and built so they are lightweight, strong, and easily removed from the concrete sections that they surround. In a precast concrete plant setting, forms must be able to withstand a good number of reuses without losing their shape. On the job site, formwork is built according to the requirements of the structural drawings and must be easily dismantled and moved as construction of the building advances. So let's take a look at the form materials. So what materials can be used? First of all, wood. Wood in the form of dimension lumber and plywood sheathing is the most widely used material for building forms because of its good strength to weight ratio, workability, relatively low cost, and reusability. So also the development of exterior grade plywoods has provided a strong and durable product that is ideal for sheathing in formwork. With its large, smooth surface, strength, resistance to change in shape when wet, and ability to withstand rough usage without splitting, plywood is indispensable as a form sheathing material. An additional advantage of using plywood as sheathing in formwork is its ability to bend, thus making it possible to produce smooth, curved surfaces. So, and please refer back to the textbook and you can see the minimum bending ready for plywood panels, how that goes across grain and parallel to the grain. So then we're moving to steel, and that is also widely used as material for making forms because of its strength and durability. Steel angles and bars are used extensively as supporting members for form panels faced with plywood sheathing. Steel corner pieces used in connecting panels are popular because of their strength and reusability. So again, please refer to the textbook. There are images showing how that actually is done in the field. And we're moving to plastic. Fiberglass reinforced plastic is another material that has been used successfully as a forming material because of its moldability, lightweight, strength, and toughness. It's used in components where reusability is a factor. Standard form shapes such as dome pans for two-way ribbed slabs are its most common application. And we're moving to the next material, and that is aluminum. Although expensive compared with the other materials, aluminum is still used as a structural framing material because of its lightweight. Extruded eye-shaped sections are used as beams for supporting slab formwork as it wails on wall formwork. So also there are form liners and they serve two purposes. The first one is to improve stripping of the form from the concrete surface without damaging the form material or the concrete, and two, to produce a desired texture on exposed concrete surfaces. So, and you can see images here showing like different patterns on concrete surface resulting from the use of form liner. Then the last one is insulating board. So a special case of the insulated concrete forms, or ICF. Formwork consists of interconnecting dense polystyrene blocks that serve as a formwork for resulting grid work of reinforced concrete. The grid is first formed with conventional reinforcing steel, both horizontally and vertically, and then concrete is pumped into the insulated voids and surrounding the reinforcing steel. So the insulated formwork remains in place and becomes part of the structure, insulating both the interior and exterior surfaces of the wall. So we are moving to the next section, and that is formwork principles. The principles behind good formwork are based on the same basic frame theories used in the design and construction of permanent structural frames. Formwork must be able to withstand construction forces that, in many respects, can be more severe than those experienced by the completed structure. So it's imperative that each component of the formwork be erected according to the formwork drawings to ensure that all construction loads are safely supported. So from a construction point of view, formwork must be economical and practical to build. A number of important factors should be kept in mind when designing and constructing formwork. So forms must be strong enough to withstand the pressure of plastic concrete and to maintain their shape during the concrete plastic placing operation. Forms must be tight enough to prevent wet concrete from leaking through joints and causing unsightly fins and ridges. Forms must be as simple to build as circumstances will allow. Forms must be easy to handle on the job. Form sections must be of a size that can be lifted into place without too much difficulty and transported from one job to another if necessary. Forms must be made to fit and fasten together with reasonable ease. The design must be such that the forms or sections thereof may be removed without damage to the concrete or to themselves. And forms must be made so that workers can handle them safely. So when we talk about formwork loads and pressures, the basic consideration is that the form's ability to support without excessive deflections all loads and forces imposed during construction. And there are two types of problems that may arise. One is horizontal forms must support gravity loads based on the mass of the concrete, the construction crew and equipment, and the weight of the formwork itself. And then the second problem is that the vertical forms must primarily resist lateral pressures due to a particular height of plastic concrete. So when we talk about formwork loads, there are two types of gravity loads that are considered in the design calculations, dead loads and live loads. So the adequate bracing must be provided for all formwork to ensure lateral stability of the formwork in all directions during and after the placement. Wind loads must be considered on vertical formwork in particular. However, formwork supporting slabs must also be stabilized against the forces due to wind and equipment. So concrete pressure on formwork, the lateral pressure exerted by plastic concrete on vertical formwork is rather complex in nature and is affected by several factors. So um, the temperatures of concrete and atmosphere affect the pressure because they affect the setting time. When these temperatures are low, greater heights can be placed before the concrete at the bottom begins to stiffen, and greater lateral pressures are therefore built up. Vibration increases lateral pressures because the concrete is consolidated and acts as a fluid for the full depth of vibration. So refer to the textbook. There is a formula and there are some calculations for the maximum pressure for design of wall forms. You should not memorize it, but that's something that you should keep in mind when designing. And also, you can see the maximum lateral pressure for design of column forms. So there's like another chart here. So please just always keep that somewhere where you can access that. And we're moving to the rate of placement. The rate of placement depends on the type of equipment that is being used to distribute the concrete. A concrete pump is the most efficient way to place concrete in that the concrete can be placed continuously. In the case of walls and columns, this can result in relatively high concrete pressures on the formwork. Rate of placement is normally expressed in feet or meters in the metric system of concrete placed per hour. And typical examples for calculating placements are actually shown here in the book. So please refer to that and see how the problems are solved. And we are moving to concrete pressure calculations. Again, once the rate of placement has been calculated and the temperature of the concrete determined, the pressure calculations proceed. So you can see the examples that illustrate the pressures that may result based on typical placement rates and placement temperatures. So again, there are some diagrams and some calculations and graphics showing how to do that. So please refer to the book because we're just providing the high level overview here. We're moving to the next chapter, and that's formwork design. So in order to take full advantage of sawn lumber sections and plywood sheathing, as formwork materials in the construction of wall and column formwork, two methods of framing are commonly used: forms without studs and forms with studs. For design purposes, formwork without studs can be divided into the following components: form sheathing, wales, ties, and lateral bracing. So here again, you can see the section, and you can see how that actually is designed. You can see the wales that go across and then that form tie in tension due to concrete pressure. You can see the diagonal bracing. You can see sheathing, and the pressure goes towards the sheathing due to concrete. And then you can see the concrete footing as well. So when the concrete pressure within the formwork increases to a point where the spacing of the wales becomes impractical, studs are added to the framework of the form to support the sheathing. And then you can see here, and the breakdown of the forming system then becomes a little different. So that's form sheathing, studs, wales, ties, and lateral bracing. So here again, you can see how that is composed. You can see different spans, different sections, and please refer to that so you know how it's actually illustrated. So forms supporting gravity loads are also composed of components similar to those for walls and columns, and they include form sheathing, joists, beams, shores, mud sills, and lateral bracing. Again, illustrations that actually speak 1,000 words here. Formwork tables. To facilitate the design of formwork components, the American Concrete Institute has developed a series of tables that provide a designer with a quick method for selecting the appropriate size of section for a particular loading situation. And again, there is a chart showing safe spacing of supports for plywood sheathing, continuous over 4 or more supports. And again, there's nothing to memorize. It's something for your reference. When you design, you should always refer to those charts because they have been pre-calculated, and that's how you can utilize them in your design. So, and we are moving to the next section, and that is footing forms. So usually two factors are of prime importance in considering the construction of footings. One is that the concrete must be up to specified strength, and the other is that the footings be positioned according to plan. The appearance is seldom of importance as footings are usually below grade. Old or used material may be employed for footing forms provided it is sound. A certain amount of tolerance is allowed in footing size and thickness, but reinforcing bars and dowels must be placed as specified. Concrete is sometimes cast against the excavation, but care must be taken that this does not give inferior results caused by the earth absorbing water from the concrete or by pieces of earth falling into it. Again, images illustrating simple footing form and heavy grade beam form, then stepped wall footing, how that is actually placed, and simple column footing form. So tapered footing forms are made like a hopper. Cleats hold the side and the end sections together, and some convenient method must be used to hold the form in place. Two opposite panels are made to the exact dimension of the footing face, whereas the other two must be sufficiently longer to accommodate the thickness of the plywood and the width of the cleats used. So again, please see the pictures. You can see how that is arranged on site or in the factory setting. Uh, and we are moving to the next sub-chapter, that is wall forms. So wall forms are made up of 5 basic parts: sheathing, studs, wales, braces, and ties and spreaders or tie spreader units to hold the sides of the form at the correct spacing. So again, refer to the picture. If we talk about built-in place forms, um, it can be done when the design of the structure is such that prefabricated panels cannot be adapted to the shape, or when the form is for one use only and the use of prefabricated panels cannot be economically justified. The first step in erection of wall forms of any kind is to locate them properly on the foundation from which the wall will rise. This may be done by anchoring a sole plate for either the inside or outside form to the foundation with preset bolts, concrete nails, or power-driven studs. It must be set out from the proposed wall line by the thickness of the sheathing to be used and carefully aligned. Another method of positioning the form is to anchor a guide plate to the foundation in such a position that the forms will be properly located when they are set behind it. Um, Again, you can see here some typical form tie installations such as rod tie, short coil, then pipes, coil ties, clip ties, snap ties, and so on. So if the guide plate method of locating forms is used, section of inside and outside forms can be built, tied together and set in position, ready to be bolted or clamped to adjoining sections. So Also, what else is important to remember here is that plumbing is the final operation in building a wall form. Many bracing systems have some means of adjusting the braces while the form is being plumbed. If braces are not adjustable, the wall must be plumbed as the braces are installed and anchored. If one form is plumbed as soon as it's built, there is no need to plumb the opposite side. The second form will be plumbed automatically by the ties and spreaders. So when we talk about the prefabricated forms or prefab, a majority of the formwork being erected is done with the use of prefabricated form panels. These can be reused many times and reduce the time and labor required for erecting forms on the site. So many types of prefab form panels are in use. Contractors sometimes build their own panels from wood framing covered with plywood sheathing. A standard size is 2 by 8 feet, but panels can be sized to suit any particular situation. Here you can see the formwork panels. Supported by double 2x4 wales, and you can see the wall form section made from the panels. So giant panels and gang forms. So high walls in which the concrete will have to be placed in 2 or more stages or lifts will normally be formed by the use of giant panels, and they're larger than the normal 2 by 8 feet or 4 by 8 wood panels, or by gang forming, making up large panels by fastening together a number of steel frame panels. A special type of steel frame panel is made specifically for gang forming. Again, you can see the illustrations here, how that is made. So these large forms are built or assembled on the ground and raised into place by crane. The basic differences between them and regular form panels are their size, the extra bracing that is required to withstand handling, and the fact that they require lifting hardware. Manufacturers of steel frame panels also supply lifting brackets, which are attached to the top edge of the gang form, but wooden panels have to be fitted with lifting hardware. And you can see the illustrations here. So special attention must be given to corners when forms are being erected. These are weak points because the continuity of sheathing and wales is broken. So forms must be pulled tightly together at these points to prevent leakage of concrete. So again, please refer to the images. You can see the corner rods and eyes. You can see corner brackets and tie rods. So how that works together. We are moving to the next subsection, and that is slip forms. And those are a type of form that could be compared with a set of dies originally designed for curved structures such as bins, silos, and towers, for which the conventional forming systems were not suited. They are, however, increasingly used for a variety of structures, including rectangular buildings, bridge piers, and canal linings. So slip forms consist of an inner and outer form, and they can be fabricated from wood or steel to produce the desired building shape and supported by 2 strong vertical yokes. These yokes are tied together across the top to give the form sides the rigidity needed uh, to produce reasonably smooth surfaces. So the bottom ends of the form sheathing are slightly tapered to make actually to help make the forms self-clearing. Again, there is a section showing the schematic diagram of slip form, how that is used. So instead of remaining stationary as normal forms do, slip forms move continuously upward, drawn by jacks climbing on vertical steel jack rods. These are anchored at the base of the structure and embedded in the concrete below the forms. The jacks may be hydraulic, electric, or pneumatic and are capable of producing form speeds of up to 20 inches. So if the jack rod is to be reused, it is withdrawn from the wall after the forming is complete. Concrete is placed into the forms at the top end, and as they are drawn upward, they act as dies to shape the concrete so that it emerges from the bottom of the form shaped as planned and set enough to carry its own weight. Um, so this is a continuous process, and filling and moving the forms upward often 24 hours a day until the structure is complete. So the operation may be stopped and resumed later, resulting in the same kind of concrete joint that one would get between lifts in conventional form use. So openings in the wall may be formed by introducing neatly fitting bugs into the form at the proper location. Beam pockets, key slots with dowels, and anchor slots for attached masonry can also be placed in the same way. Also, the success of a slip forming operation depends on good planning, design, and supervision so that the operation may be as continuous as possible. And some of the major factors contributing to successful slip form construction are the following. So you need to have the proper concrete mix design and careful control of the concrete to maintain the proper slump and set in spite of changing temperatures. Then adequate facilities are required for supplying concrete to the forms at any height, and adequate concrete supply is also needed. A supply of reinforcing steel at hand and experienced workers to do the fabricating as work progresses. Then reliable forms designed to stand the stresses placed on them by the constant heat or liquid concrete, and supervisors who thoroughly understand the operation of slip forms. So that is another necessary factor that contributes to the successful erection of the slip form wall. And we're moving to the next subsection, that is construction joints. So it is often necessary to place long or high walls in sections. This results in a vertical joint. There are two sections of a long wall, where two sections of a long wall meet, or in a horizontal joint when high walls are placed in two or more lifts. Such joints are called construction joints and require special attention. So where vertical construction joints are formed by placing a bulk head in the form, it may be one piece or material, of material placed vertically in the form of a number of short pieces placed horizontally. The latter is preferable when horizontal reinforcing bars project beyond the bulkhead because the pieces can be cut to fit around the bars. So, there are a few methods of securing the bulkhead shown here in the diagrams, so please refer to the images. So two important factors are involved when making horizontal construction joints. One is the necessity of having the two concrete lifts bond at the joint, and the other, in certain cases, is the requirement that the joint be invisible or as inconspicuous as possible. When the form for the first lift is built, a row of bolts is placed near the top of the lift. After this placement has set, the forms are stripped and raised as required for the next lift and supported on bolts placed in the top holes previously cast. A row of ties should be placed around 6 inches above the joint between the lifts to prevent leakage and help make the joint inconspicuous. So hiding of horizontal construction joints is often accomplished by the use of rustication strips. These are narrow strips of various shapes nailed to the inside face of the form at the level of the joint. Concrete is placed to a height slightly above that required and then cut back to it. And again, there are some illustrations here, so please refer to the textbook. We're moving to control joints. So control joints in concrete are made to control cracking due to contraction. They are formed by fastening a beveled insert of wood, metal, rubber, or other material to the inside face of the form. The insert produces a groove in the concrete that will control surface cracking. After the concrete has set, the insert may be removed and the joint caulked. Rubber inserts may be left in place. When a water stop is required at the control joint, a rubber stop is often used. So we are moving to the column, girder, and beam forms, and that actually is similar to how actually the formwork is used for footings and the walls. So as far as the floor forms, the design of forms for concrete floors depend a great deal on whether the floor is a slab on grade or a structural slab supported on a steel or concrete structural frame. So let's take a look at the slab on grade forms. They're usually quite simple. Concrete is cast on a compacted earth or gravel base, and forms are required only for the edges. Plywood, planks, or steel edge forms are commonly used for this purpose. Wood forms may be held in place by wooden stakes or by form supports, such as the support bolts. The plank can be adjusted for height by turning the bolt up or down. So steel edge forms are commonly used on larger jobs and for highway work. Provision is made for the wheels of mechanical strike-off bars and floats to ride on the top flange of steel edge forms. So again, there are illustrations showing how that actually is done, showing the steel slab edge form, showing the T-bar screed support, showing the slab form support, and others. So to ensure a correct thickness of slab, the subgrade is normally leveled with a fine graded granular material compacted to its maximum density. In the past, the use of vapor diffusion retarders, commonly called as vapor barriers, under all slabs on grade was considered to be good practice. Recent research into the effectiveness of these barriers has brought their use into question. Improper placing and vulnerability to puncturing during concrete placement brings the use of vapor retarders under slabs into question and defeats their use in many instances. So in some situations, it has been found that these films cause stressing in the slab due to non-uniform dyeing and curing. It is recommended that for slabs on grade that are sealed with some type of covering such as vinyl, tile, carpet, or wood, a vapor retardant should be installed. To achieve proper performance on the of the slab on grade, each slab should be evaluated according to the site conditions and its end use. The reinforcement in slabs on grade may or may not be specified depending on the slab area and the use of control joints. Reinforcement in the form of reinforcement bars or rebars or welded wire reinforcement, commonly called wire mesh, is often used. The ACI, or American Concrete Institute, recommends a minimum of 0.2% steel to concrete ratio in each direction for normal applications. If this minimum is followed, reinforcing bars are usually preferred because of better placement and location control during the concrete placement. To ensure the proper location of the reinforcement above the base, chairs, bolsters, and spacers made of either metal or concrete can be used. Bolsters do not space bars and can be used anywhere, and spacers are made to order to provide a leg under each bar, whereas bar chairs may be used as required. And again, there are some illustrations showing how that works, showing those little individual bar chairs and continuous high chairs as well. So if strike-off bars cannot reach from one edge of a slab to the other, it will be necessary to set up screeds or temporary guides in the slab area to be used to bring the concrete being placed to the correct grade. Wood screeds may also be supported by adjustable screed supports, such as here made of plywood. Straight pipe may be used as a screed, or small pipe or T-bars on adjustable supports used to support wooden screeds. Again, please refer to the images. You see the construction joint forms, and wood and metal ones are shown. Forms for control joints, which control the location of cracks that inevitably occur in a concrete slab as a result of shrinking of the concrete, may be made in several ways. One common method is to insert a wood or metal strip into the slab, top or bottom, to form a plane of weakness. Another method is to make a cut partway through the slab with a masonry blade. Another method is to set two structural steel angles into the slab surface so that a plane of weakness is established below them. And again, you can see the different types of control joints here. Concrete is rarely larger in volume than when it's first placed. As a result, true expansion joints are rarely necessary in slab construction. Expansion joints are mostly effective in long, narrow placements of concrete, such as sidewalks and other pavement sections. Although commonly called expansion joints, isolation joints are used to separate one placement of concrete from another, such as for infill slabs or masonry or concrete walls, column blockouts, and curb on pavements. Often, though, to be necessary for the mitigation of the expansion of one concrete sample against the other, they're actually used to allow movement of one section relative to the other without regard to the direction of that movement. It's only in very rare cases that the thermal expansion of concrete exceeds its drying shrinkage. So the same result may be accomplished by using a strip of compressible material. Usually it's asphalt impregnated fiberboard, and leaving it in that position. So Again, please refer to the images how that actually works. We're moving to the structural slab forms. Forms for concrete decks, floors above grade, supported by a structural frame, will be as varied as the systems that support them. In some cases, such as cast-in-place reinforced concrete frame, columns, beams, and slabs, will be cast monolithically, and forms must be designed accordingly. In the case of a precast concrete frame, deck forms may not be necessary, depending on the type of members used. For example, single or double T provides the floor topping slab form and the frame. A structural steel frame will require deck forms for the floors. So when we talk about beam and slab forms, they incorporate the forms for the spandrel beam, the regular girder, the beam forms, and the slab forms. Support systems for these forms include wood T-posts, adjustable metal posts, and supports made with metal scaffolding. So when we talk about flat slab floor form, that is the system in which there are no beams and no drop panels. The first story columns are usually cast first, then the slab forms are set up for the floor that they will support. And when the floor is ready, the operation is repeated for successive floors. When we talk about ribbed slab floor form, they are formed by the use of metal pans resting on the flat deck or supported by joists. The pan system may be supported in a number of ways. And again, please see the pictures, how that is done in the field. Waffle slab floor is formed by using dome pans or of metal or plastic resting on a flat deck. So, and you can see again, there's a picture showing the placement of those pans. Pre-stressed concrete joist floor form. So the design of a floor framed with pre-stressed concrete joists may specify pre-stressed concrete planks for the floor slab. On the other hand, the floor may be a cast-in-place concrete slab placed on a slab form suspended from the joists. Steel frame floor forms. So floor forms for concrete floors supported by a steel frame will vary depending on whether or not the fireproofing for the steel beams is to be cast monolithically with the slab. In either case, in either case, the slab forms will usually be suspended from the steel frame, eliminating the necessity for a shoring system. And we are moving to the flying forms. So the building consists essentially of either a series of columns supporting flat plate floors or a number of shear walls doing the same thing. A floor slab form and its support system designed for one floor can be reused for all the other forms. The main problem being the moving of the forms from one position to another. This problem has been solved by the use of flying forms, which are forms designed as complete units large enough that the entire floor of one bay may be cast on it and capable of being moved as a unit from one position to another. So again, a few beautiful images here. And the form is lowered onto rollers, the flying form. The jacks folded up into the flying position and the form rolled out of the bay to where it can be hooked to a crane, which will finish moving it out of the bay and swing it into a new position. There it will be used again and moved again as many times as there are bays in the structure that form will accommodate. So, and please see the sequence of operations here. Just review the images here. So when we talk about shoring systems, so shoring members are used to support concrete forms and their contents of other structural elements and may be divided into two major categories, horizontal and vertical. So horizontal shores range from small units, such as those that might be used to span between pairs of precast concrete joists to support the plywood deck form, to large wood or steel members with relatively few supports used to carry much heavier loads with a minimum of interference in the work area below. Vertical shores are those that support the horizontal ones from a firm base below, such as a concrete slab or mud sill, if there is no solid bearing on which the shore may rest. So they may be of wood or metal and take many different shapes depending on the particular circumstances. And again, please see the pictures here. We are moving to shoring and reshoring in multi-story structures. And then we'll have the form accessories left, and that will be it for this chapter. So when building multi-story structures using cast-in-place concrete, the rate at which the structure advances is controlled by the ability of the placed slabs to support load. For a contractor to wait for fresh concrete to develop its full strength before continuing to the next level would be an inefficient use of time. So, shoring and reshoring semi-cured slabs allow the contractor to transfer the construction loads through the shores without affecting the freshly placed sections. The amount of shoring and reshoring depends on the strength of the partially cured slabs, the amount of load that is to be transferred to each slab, and the rate of advance that the contractor wishes to achieve. Although the operation appears to be straightforward, the loads transferred from one shoring to the slabs can be much higher than expected, and once a sequence has been decided, it should be followed by the duration of the followed for the duration of the job. So again, please take a look at the images, how that is being constructed. So the first floor shores are supporting the dead weight of the two floors above. Once the second floor slab is cured and gains strength sufficiently, part of the first floor shores may be removed. Each slab must support its own weight, and before any construction loads are applied to the second floor, reshoring is placed under the first floor to ensure that no additional loads are applied to the first and second floors. While the original shoring is done based on spacing required for total load support, the placement of reshoring is more strategic to obtain the benefit of the structural capacity of the formerly um, fully supported components to help support subsequent loading from the construction activities. Once the third floor has set, the first floor reshores can be removed. The load on the first floor reshores, that's the dead weight of the third floor, is now redistributed among the three slabs. The remaining shores must now support that load above them, not supported by the slabs. The first and second floor slabs, as a result, support 1/3 of the third floor weight each. So removing the second floor shores redistributes the load carried by the shores between the two interconnected slabs. The third floor slab now supports half of its own weight, and the second floor slab supports its own weight and half of the third floor, and so on. So this can continue up to the next levels. So we are moving to the form accessories. There are a few of them, and this will be the end of our chapter. So the form accessories include items that have already been mentioned in the chapter, such as ties, spreaders, wedges, corner brackets, and whaler clips. And they can also include snap ties for special conditions, rock anchors, beam hangers, water stops and keys, masonry ties, column clamps, shores, form rods, concrete inserts, sleeves, slab pans, and many others. So in nearly all types of building construction, formwork constitutes a significant part of the cost of the building. To keep this cost at a minimum, forms are often made reusable, either wholly or in part. They must therefore be designed so that removal is simple and can be accomplished without damage to the form sections. To facilitate removal, form faces must be treated to prevent concrete from adhering to them. A number of materials are available for this purpose, usually consisting of liquids that are to be brushed or sprayed on the form. Wooden forms must be treated to minimize absorption of water. Oil is one of the materials used for this purpose. Form sealers that coat the surface of the form with an impervious film are also used for this type of treatment. So the production of concrete structures of the desired size, shape, and strength, yet pleasing to the eye, can be achieved if a number of important points are remembered. So forms must be properly designed and carefully constructed and erected. They must receive the appropriate surface treatment. Tying, bracing, and shoring must be adequate for the particular job involved, and there must be proper handling, placing, consolidation, and curing of the concrete, and form removal must be carried out in such a way that no damage is incurred by the finished product. So that was it for our chapter 6. Thank you so much for watching. I'll see you in chapter 7.